Hi everyone. Now I'm going to talk my paper called MOVERY, a precise approach for discovering propagate vulnerable code from modified open source software components. I'm Seunghoon from Korea University. Hyunji, Eunjin, Choi, and Heejo also worked together to write this paper. So the reuse of open source software project becomes a trend in recent software development because developers can reuse their desired functionalities from the rich OSS pool. Despite the advantages, unmanaged OSS reuse can produce several problems such as vulnerability propagation. Since the propagate small code fragment can compromise the entire software security, many existing approaches attempt to detect the propagate vulnerable code. But however, recently most developers reuse OSS project with code or structure modifications, especially in the languages that code level use is prevalent, such as C and C++. So it is very difficult to discover propagate vulnerable code with code changes. Therefore, the main research question of our study is how can we precisely discover propagate vulnerable code with various syntaxes? We found that the two major reasons for the syntax diversity of propagate vulnerable code, internal and external modifications of OSS. So the OSS source code frequently changes during the OSS updates. In this context, a vulnerable code may propagate to other software with the different syntaxes depending on the reused OSS version. And also, developers can change the syntax of the vulnerable code during the OSS reuse process. So this is an example syntax diversity caused by the internal OSS modification. This DOS vulnerability originally existed in the Lua code base, and then it propagated to the Redis code base, which reused the vulnerable version of Lua. Although those two functions contain the same vulnerability, we can see that the syntax of two functions is quite different owing to the internal modification. So the Lua development team fixed this vulnerability in Lua 5.2.3, but the Redis team reused much older version of the Lua 5.1. So because of the multiple OSS updates between the two versions, the syntax of propagate vulnerable code exhibits a different syntax with the disclosed vulnerable function. Owing to such syntax diversity, existing approaches fail to detect this kind of propagate vulnerable code. One example is redebug, a vulnerable code detection approach that considers nearby 3 lines of deleted and added code lines from the patch. So in this case, they consider the seven code lines in the left code snippet as the signature, but the propagate vulnerable code does not contain the 7 code lines, so redebug failed to detect this vulnerable code. And the other example is buddy, a scalable approach for detect propagate vulnerable code. Buddy considers a whole vulnerable function as the signature. But in this case, obviously, the syntax of the two vulnerable functions is quite different, so Buddy also misses this vulnerability. To overcome this problem, we present MOVERY, a novel approach to precisely discover propagate vulnerable code with various syntaxes. So the two key techniques used in MOVERYs are function collation and core line extraction. Before I will introduce the mechanism of the MOVERY, we first let us assume that the oldest vulnerable function as FO, and after several OSS updates, the disclosed vulnerable function as FD, and after applying the patch, let's define the patched function as FP. So MOVERY first generates vulnerability and patch signatures for a vulnerability, and then try to discover the propagate vulnerable code by using the generated signatures. So I will introduce the mechanism of MOVERY by using the working example. The heap buffer overflow vulnerability existed in Jasper. So this is the patch snippet of the vulnerability. So MOVERY first collates the oldest and the disclosed vulnerable function. And by collating the two functions, MOVERY extracted only the core lines that are directly related to the vulnerability manifestation. Specifically, MOVERY considers the following 3 types of core lines: essential, dependent, and control flow code lines. So the essential code lines refer to the code lines that are deleted from the patch and exist in both the oldest and the disclosed vulnerable functions. And dependent code lines indicate the code lines that have control or data dependencies with the essential code line. And last, the control flow code lines refer to the control statement that exists in both the oldest and the disclosed vulnerable function. So MOVERY first extract the essential code lines from the patch. So among the 3 code lines that were deleted from the patch, only the line number 9 is contained in both the oldest and the disclosed vulnerable function. So MOVERY extracted the line number 9 as the essential code line. And next, MOVERY extracts the dependent code lines from the code. So MOVERY considered the dependent code lines to determine whether the vulnerability trigger environment has also propagated to the target program. So in this case, the line number 8, which has the control dependency with the essential code line, and the line number 14, which has the data dependency with the essential code lines, are extracted as the dependent code lines. And finally, MOVERY extracted the control flow code lines. So sometimes developers try to resolve the propagate vulnerable code by adding some conditional statement into the vulnerable function, such as code sanitization. So MOVERY considered the control flow code lines to determine whether the essential code line has to be reachable with the same conditions used in the original vulnerable function. So in this case, the line number 3 and also the line number 8 are extracted as the control flow code lines. So by gathering all the essential, dependent, and control flow code lines, MOVERY generates the vulnerability signature of this vulnerability, a set of core code lines. And then MOVERY also generates the patch signature by using the similar approach that is used in generating the vulnerability signature. But in this case, instead of consider the code lines that are deleted from the patch, MOVERY consider the code lines that are added from the patch. And after generating the vulnerability and patch signature, MOVERY then tried to discover the propagate vulnerable code. So if a function f in the target program satisfies all the following 3 conditions, MOVERY determines that the function f is the propagate vulnerable code. So if f contains all the code lines in the vulnerability signature, if f does not contain any code lines in the patch signature, and if the syntax of f is similar to the oldest or the disclosed vulnerable functions, MOVERY considers that f is the propagate vulnerable code. So to measure the syntax similarity between 2 functions, we used the Jacquard index by considering the function as a set of code lines. To evaluate MOVERY, we collected more than 4,000 CVE patches from the MVD, and we selected 10 target programs that are popular and contain a sufficient number of OSS components. So the selected 10 target programs is summarized in the table. And we selected the threshold zeta as 0.5, which is used in measuring the syntax similarity between 2 functions. And also we selected 2 comparison targets, redebug and buddy. And when we applied redebug, buddy, and MOVERY to the selected 10 target programs, they could discover 434 propagate vulnerable code from the selected target programs. We confirmed that MOVERY significantly outperformed the redebug and buddy because MOVERY could discover more than 400 vulnerable code with 96% of precision and recall. But redebug and buddy, which did not fully consider the OSS modifications, failed to discover many correct propagate vulnerable code. So in particular, MOVERY could discover 2.5 times and 5.8 times more vulnerable code than redebug and buddy. In particular, the following 3 types of vulnerable codes were hardly discovered by redebug and buddy. So if the propagate vulnerable code does not contain all the code lines deleted in the patch, if the propagate vulnerable code was derived from the oldest vulnerable function, or if the propagate vulnerable code has undergone heavy syntax changes, existing approaches fail to detect the propagate vulnerable code. But MOVERY which collate the oldest and the disclosed vulnerable functions and considers only the core lines, can address these types of propagate vulnerable code. So this is the conclusion. We found that many vulnerable codes are propagated with syntax modifications. Actually, the 91% of the discovered propagate vulnerable code exists in a different syntax to the disclosed vulnerable function. So to precisely discover the propagate vulnerable code with various syntaxes, we present MOVERY. And from our experiment, we affirm that MOVERY outperformed existing vulnerable code detection approaches. Yeah. So this is the end of my presentation. Thank you for your attention. And if you have any questions, please feel free to ask me. Thank you.